Now we will see another example of centripetal force. Uh, in this case, we are going to study the backing of an airplane or tilting of an airplane for a turn. So airplane taking a turn. Airplane taking a turn. It's usually called banking. Taking a turn. Sometimes it is called banking of airplane. For this, the wings of the airplane has to tilt to make the plane turn. So let us see how the forces act in this case. Now the case is obvious. You need a centripetal force to make the airplane turn. So we'll see how we are going to get the necessary centripetal force by tilting the wings. So let us see. We will draw a functional diagram here. It doesn't look like an airplane. Don't worry about it. It's only for the purpose of getting all the forces on the plane and see how we get a centripetal force in the end to make the airplane turn. So that is the wing. Okay, now we have the fuselage. Okay, let us say this is the body of the airplane. Okay, it doesn't look very nice. I'm sorry about it. Try to make it look a little bit okay. Right. Here we go. That's the body of the airplane. Not very happy about it. Wait a minute. It should be near the center. So it doesn't really matter because the purpose is just to get all the forces marked and see where we get the centripetal force from. Okay, that's the body of the airplane. Now this point we can consider as the center of mass of the airplane. Now the first force that acts obviously is the weight of the airplane acting downwards. So let's mark all the points with a different color. So we use which color I don't use about something which looks pretty fine. No. Okay, let's do that. So here we have the weight of the airplane acting downward. So this is the weight of the airplane acting downward. Let's make it a little bit short. Okay, here we have. Should be perfectly vertical. If it doesn't look perfectly vertical, I'm sorry about it. W, that's equals to mg. This is the weight of the airplane acting downward. And the second force that acts on the airplane is the lift provided by the wings. The lift acts normal to the wing, so I can mark it here. Here we have the lift. Okay. All right, here we have. That should be perpendicular to the wings. So I'll mark it as L. Here we have L, that stands for the lift of the airplane provided by the wings. Because the wings are tilted a little bit to provide the centripetal force. Now, as a result of these two forces, there should be a net force acting toward the center of the curvature. Now, let's assume that the airplane is turning in this direction. This is the direction in which the airplane turns. So the center of curvature comes somewhere here on the left side. So I can mark it as C if you want. This is the center of curvature of the turn. And now we can draw the vertical line to show that we measure all the angles along the vertical and the horizontal. So we use a different color for this. I don't know, I'll just use this color. Okay, let's have this color. So this is the vertical line. Just the vertical, sorry. Okay, here we have the vertical line. This is the vertical line. So the vertical angle you can take as theta in this case. So this is the vertical angle theta. All right. Now, the component of the lift, we can mark here. This is the vertical component of the lift. This is the vertical component of the lift. All right. Put an arrow in here. You can write it as L cos theta. This L cos theta must balance the weight. And we have the horizontal force, horizontal component of the lift acting towards the left. Here we have the horizontal component. So let's put an arrow in here to show the direction of the horizontal component, and we can write it as L sine theta. This should provide the centripetal force to make the plane turn. Now let us write all the equations here and see what is the optimum speed at which the plane negotiate a curve, or rather take a turn. So we can write here L cos theta, which is the vertical component of the lift that must be balancing the weight. So you can write it as mg. Put it as equation number 1. Here we have equation number 1. And the horizontal component of the lift should provide the centripetal force. But you can write L is L sine theta is equal to m v square over r. Put it as equation number 2. Now we can divide equation 2 with equation 1. So we'll write equation 2 divided by equation 1. And you will get tan theta is equal to v square over rg, or the optimum speed v to turn the airplane is given by square root of rg tan theta. In this case, we did not take into account any of the air drag or other kinds of forces. We just took care of the relationship with two forces in action, which are the weight and the lift. So this is the explanation for the optimal speed of an airplane taking a turn by tilting the wings through an angle of theta. Now let's see another case. Case of a banked rod. Now, what does it mean by banked rod? Whenever there is a sharp turn on a rod, the outer edge of the rod is lifted up a little bit to provide the centripetal force. That's called a banked rod. So let's do the case of banking at curves. Banking at curves provides centripetal force for safe travel of a vehicle taking a turn. So banking at curves. Now let us see the case here. Now again, the road is curving in this direction. Show this. So the center of curvature of the curve is somewhere here. Let's assume that, put it as C. Now we will draw the horizontal surface on which the road is made. Here we have it. All right. Use a different color. All right, let's use. Okay. So here we have the horizontal surface on which the road is built, and the road is built with a tilt. The outer edge of the road is raised up. Here we have considerable rise to make the equations look fine. Actually, the tilt will be very small. So this edge is tilted up, and this horizontal angle is called the angle of banking. We call it theta again. Now let us draw the diagram of a vehicle taking a ride. Okay, I might use a color which right here. So let us draw a vehicle. This is just a schematic or functional diagram. It doesn't look like a vehicle. I'm trying to draw the diagram of a car. It may not look very nice, but that's irrelevant for us. It should serve the purpose. That's the only thing. I'll try to make it okay. When you look at it, you will understand. It's a car. The outer edges look like the cross section of a car, a bit like. Okay, this is a car. All right. Assume that this is a car at least. Oh, I'm not very happy about it. Problem is making these diagrams look decent. Not always very easy with freehand diagrams. But at least it serves the purpose. I need to draw the two tires. I'll just draw them here. These are the two tires that touches the road. Sorry, it doesn't look very nice. Okay. Here we have the two tires. Okay. That's a car. Now let us mark the center of mass of the car somewhere here. So I'm going to plot all the forces at the center of mass. Even though the reaction forces are acting on the tires, I'm just going to plot the net reaction force on the center of mass. So first we will have the weight of the car acting downward. So here we have the weight of the car. I will mark it, the weight of the car acting downward. Okay. This is not proportional. Just the basic concept must be clear, that's all. I must use a different color, you think? So you won't get confused. Here we have the weight of the car acting downward. Okay. Put an arrow and write W. That's equal to mg, which is the weight of the car. Now we need to draw the reaction force, normal reaction force acting perpendicular to the road. So I'm going to draw it here. It should be perpendicular to the road. Hope it is nearly perpendicular. The angles are very small. Theta is very small, so you might find it a little bit difficult. Okay, what is this? This is the reaction force. I will mark it as R. Now we are going to draw the two components of the reaction force. One is perpendicular, another one is horizontal. The perpendicular component of the reaction force should match the weight of the car. So here we have the perpendicular component of the reaction force. Yeah. This is perpendicular, sorry. The vertical component of the reaction force, we can write it as R cos theta. That should balance the weight. And then we have the horizontal component of the reaction force acting in this direction. This is not exactly proportional to the actual value. I'm sorry. The only purpose is to make the idea clear. So this is the horizontal component of the reaction force. I can write it as R sine theta. This force provides the centripetal force. This is the centripetal force. Now we are ready to write the equations in here. As in the earlier case, we can write R cos theta is equal to mg. Equation number 1. All these equations are similar because the forces we take are similar and the angles we take are similar. That's why R sine theta is providing the centripetal force. So you write R sine theta is equal to m v square over R. So put it as equation number 2. Now, as in the previous case, you can divide equation 2 with equation 1. So, equation 2 divided by equation 1. So, you would get tan theta is equal to you will get v square over rg. Again, the optimum speed v is equal to square root of r g tan theta. Here, v is the optimal speed. What does it mean by optimal speed? We call it optimal speed or the optimum speed because even v exceeds this value, still the vehicle is safe because we haven't considered friction into this equation. Because the actual centripetal force will be slightly greater than r sine theta because still there is friction between the tires and the road. That has not been taken into consideration. So this is called optimum speed, not the maximum speed. So in all these equations, we haven't considered the friction. So what we get in these equations are all optimum speed, not the maximum speed with which you can drive the car.